Welcome to today's paper reading. Today's paper is titled, Unlimiformer, Long-Range Transformers with Unlimited Length Input. This paper was published in the 37th Conference on Neural Information Processing Systems, NeurIPS 2023, by Amanda Bertsch and colleagues from Carnegie Mellon University and Google DeepMind. The abstract highlights the limitations of traditional transformers, which are constrained by the need to attend to every token in bounded input lengths. To address this, the authors propose Unlimiformer, a method that integrates with existing pre-trained encoder-decoder transformers and employs a k-nearest neighbor index for cross-attention computations. This approach allows for the processing of practically unlimited input sequences, as demonstrated by the ability to handle inputs as long as 500,000 tokens without truncation. The evaluation shows that Unlimiformer enhances models such as BART and Longformer by enabling them to handle unlimited inputs without requiring additional weights or code modifications. Transformers, while effective, have limitations in handling long sequences due to their context window sizes typically ranging from 512 to 1024 tokens. This limitation arises from the quadratic complexity of self-attention mechanisms, making it impractical to scale naively. Long input transformers address this by either sparsifying or approximating attention, thereby extending the maximum input length while remaining computationally feasible. Unlimiformer introduces a novel approach by using a retrieval-based method to augment pre-trained language models. It constructs a k-nearest neighbor index over the hidden states of input tokens, allowing each cross-attention head to query this index for the top k relevant tokens. This method does not require adding new parameters or altering the model's architecture, making it a versatile solution for handling unbounded input lengths. Figure 1 illustrates the disparity between the input lengths of various summarization and question-answering datasets and the common context window lengths of transformer models. The figure highlights datasets with inputs exceeding 500,000 tokens, which are significantly longer than the typical maximum input lengths of 1024, 4096, and 16,384 tokens. Notably, the longest inputs are more than 34 times longer than Longformer's context window, underscoring the challenge of processing extremely long sequences with traditional transformer models. Figure 2 illustrates the Unlimiformer architecture, which allows a language model's encoder to handle inputs longer than its maximum input length by encoding the input in chunks and indexing them. Unlimiformer is injected into each decoder layer before cross-attention, where it performs a k-nearest neighbor (KNN) search to select a two-token context for each attention head from the index. This enables cross-attention to attend to tokens from the entire input sequence without adding parameters or altering the given language model's architecture. Unlimiformer introduces a novel approach to transformer models by allowing each cross-attention head to select distinct keys from the full-length input at each decoding step. This is achieved by integrating a KNN search into each decoder layer. The encoding process involves chunking the input sequence and indexing the encoded vectors in a KNN index. The attention mechanism is reformulated to store a single index, enabling efficient retrieval and significant space savings. This approach not only enhances the model's capability to handle long sequences but also reduces computational and memory costs. The training of Unlimiformer can be categorized into low-cost and long-range methods. Low-cost training includes using Unlimiformer only at test time, during early stopping, and through chunk training. Long-range training involves random encoded, retrieval, and alternating training methods. These approaches aim to improve the model's performance with varying computational costs. Additionally, the experimental settings section outlines the datasets used, their input length distributions, and specific training details. Table 1 provides a detailed comparison of various training approaches for the BART model, which has a context window size of 1024 tokens. The table categorizes these methods based on their training input token counts, ranging from 1024 to 16K tokens, and their test input token counts, which can be unlimited. The dashed line in the table distinguishes between methods that have a similar training time cost to the baseline and those that require significant additional computational resources. This comparison is crucial for understanding the trade-offs between computational efficiency and the ability to handle longer sequences during training and testing. Table 3 presents the results of long document summarization using low-cost training methods. It highlights that Unlimiformer enhances BART-based performance by 1.8 Rouge 1 points on both GovReport and SumScreen datasets. The method early stop with Unlimiformer further boosts the base model by 3.3 Rouge 1 points without additional training costs. Notably, Train Chunk Plus Test Unlimiformer achieves the most significant improvements, with 7.2 Rouge 1 and 3 BRT score points, while maintaining the same computational cost as standard fine-tuning. These results underscore the effectiveness of Unlimiformer in improving summarization performance without escalating training expenses. The experiments were conducted using 3 datasets: GovReport, SumScreen, and BookSum. GovReport involves summarizing U.S. government reports, SumScreen focuses on TV show recaps, and BookSum requires book-level summaries. The evaluation metrics include Rouge 1/2/L, BRT score F1, and entity mention recall. The baseline models used are BART, BASE, Primera, and SLED. BART is a pretrained seek-to-seek model, Primera is a long-former encoder-decoder, and SLED extends models for longer contexts by encoding in chunks. Table 2 provides a detailed overview of the distribution of input example lengths across various datasets. The histogram is categorized by powers of 2, clearly showing the minimum and maximum input sizes on either end of the scale. A dotted line is used to mark the mean length of the inputs, offering a quick reference point for the average size of the data samples in each dataset. The application of Unlimiformer on existing checkpoints demonstrates significant performance improvements in long document summarization. For instance, it enhances BART base by 1.8 Rouge 1 points without requiring additional training. Additionally, an early stop with Unlimiformer yields a 3.3 Rouge 1 point gain on GovReport, maintaining the same computational cost as standard fine-tuning. Notably, Unlimiformer provides the most substantial gains when applied at test time, improving by 7.2 Rouge 1 and 3 BRT score points, all while being as computationally efficient as standard fine-tuning. In comparison to other models like SLED and memorizing transformers, Unlimiformer consistently outperforms, particularly in improving base models such as BART base and Primera, and can further enhance long-range transformers like Primera. Figure 3 illustrates the performance of Unlimiformer in BookSum, showing how entity recall, ENTMET, increases almost monotonically with the maximum data store size. At all data store sizes, Unlimiformer consistently outperforms the baseline model, BART, which is highlighted in red. This suggests that Unlimiformer effectively exploits longer inputs to generate outputs with higher entity recall. The graph clearly demonstrates the advantage of Unlimiformer in scenarios where long-range modeling is beneficial, such as in book summarization tasks. Figure 4 illustrates the relationship between the maximum data store size and the inference cost. As the data store size increases, the inference cost grows but does so in a sublinear manner. The plot specifically shows the total wall clock inference time per example. This indicates that while the cost does rise with larger data stores, the increase is not proportional, suggesting efficiency in handling larger datasets. Additionally, Unlimiformer consistently outperforms the baseline, as indicated by the red line representing BART, demonstrating its superior performance in terms of inference time. Table 4 presents the test results on long document datasets, focusing on computationally expensive long-range training methods using various base models. The table highlights that Unlimiformer consistently outperforms both SLED and memorizing transformers across almost all metrics and datasets. Notably, Unlimiformer combined with BART base achieves superior performance compared to the base Primera model, despite Primera's larger size and extensive pre-training. Additionally, Unlimiformer can be applied to existing long-range transformers like Primera to further enhance their performance. The best metrics in each dataset and training category are marked in bold, with Unlimiformer results derived from the alternating training strategy. Table 5 presents the results on the BookSum dataset, which has an average input length of approximately 143,000 tokens. The table includes metrics such as rouge and entnet, which measures entity recall. Hierarchical summarization, a baseline method reported by Krasinsky et al., 2021, is also included, where chapter summaries are condensed to form a book summary. The best metric in every dataset is highlighted in bold, providing a clear comparison of performance across different models and training methods. The performance of Unlimiformer varies with input length. In BookSum, entnet scores increase almost monotonically with longer inputs, indicating that Unlimiformer benefits from longer inputs. However, in WikiSum, Unlimiformer did not show improvement over a baseline using only the first 1024 tokens, suggesting that the full input is not necessary for this dataset. Regarding computational costs, while Unlimiformer does not add trained parameters, the encoding and index search processes increase both training and inference time. The GPU time required increases sublinearly with input length, as detailed in Appendix D. Additionally, the analysis of retrieval frequency across the decoding process in BookSum shows that the number of input embeddings retrieved varies by method, with no specific pattern in retrieval locations, and the median retrieval point is consistently around the middle of the input document. Figure 5 presents a histogram illustrating the distribution of retrieved embeddings within the original document, averaged across the BookSum test set. The data reveals a slight increase in retrieval frequency in the initial 10% of the document, but overall, there is no significant trend, indicating that tokens are retrieved uniformly from the entire input. Notably, the median location of a retrieved key falls between 49.73% and 49.87% of the way through the input document, suggesting a balanced retrieval pattern across the document's length. Table 6 presents the comparative performance metrics of the BART Unlimiformer model against the base BART model across various NLP tasks. The tasks include question answering on Casper, natural language inference on Contract NLI, and query-based summarization on QMSum. The results indicate that Unlimiformer generally improves performance over the base model, particularly in the F1 score for Casper, 27.5 versus 22.0, and the exact match score for Contract NLI, 77.7 versus 77.5. However, there is a slight decrease in the rouge scores for QMSum, with Unlimiformer achieving 30.9/8.0/19.9 compared to the baseline's 30.8/8.7/20.8. The transformer architecture has seen various modifications aimed at reducing space or time requirements. Most solutions focus on sparsifying the attention mechanism, while others approximate or replace the attention mechanism entirely. These changes often require pre-training the model from scratch, which limits the ability to leverage existing pre-trained models. In contrast, Unlimiformer is designed to be generic and can be injected into any encoder-decoder transformer, either without training or with fine-tuning. This allows Unlimiformer to utilize any already pre-trained model. The closest related work is memorizing transformers, which can only apply their approach to a single decoder layer due to memory constraints. Unlimiformer, thanks to its attention reformulation, can use a single index for all decoder layers, leading to significant empirical gains. Another related work is SLED, which encodes long inputs in chunks but is limited to shorter inputs due to attending to all inputs simultaneously. Unlimiformer, by attending only to the top K input tokens, can process unlimited inputs while preserving most of the attention mass. Additional related work is discussed in Appendix G. Unlimiformer is designed to enhance pre-trained encoder-decoder models by offloading cross-attention computations to a k-nearest neighbors index. This approach allows each cross-attention head to retrieve and attend only to its top K keys, enabling the processing of unlimited length inputs. Evaluations on long document and book summarization benchmarks, with inputs as long as 500,000 tokens, demonstrate that Unlimiformer improves model performance without requiring additional training. When integrated into training, Unlimiformer not only boosts the performance of smaller models like BART to surpass larger longformer-based models, but also further enhances the performance of longformer models while reducing computational costs. The experiments conducted by the authors are limited to English language datasets. The quality of the nearest neighbor's search is dependent on the quality of the index keys, which may vary with different high-resource languages. The length of inputs during training is constrained by the GPU memory, as the embeddings and their computational graph must be stored for backpropagation. Utilizing multi-GPU training could potentially allow for longer inputs. At inference time, Unlimiformer can process longer inputs by offloading the index to CPU memory, which requires indexing only a single vector per input token. This practically allows for unlimited inputs on modern servers and even small machines. However, this method results in higher test time latency compared to storing the encoded hidden states and the index on the GPU. The authors were able to use a GPU index for input examples exceeding 500K tokens on GPUs no larger than 48 GBs, but this may pose challenges with smaller GPUs or larger models. The authors would like to express their gratitude to several individuals and organizations for their contributions to this research. Specifically, Suresh Garaja provided valuable feedback on a draft of the paper. Mawar Ivgi assisted in reproducing results from SLED and shared code and models. Yuri Shaham contributed through discussions about the scrolls benchmark. Additionally, the authors appreciate the support from 3M, M*Modal and the National Science Foundation Graduate Research Fellowship Program, as well as the useful comments and suggestions from anonymous reviewers. References to relevant works include Ivgi et al., 2022, Shaham et al., 2022, and NSF Grant No. DG 2140739. Thank you for watching.